All right, so now we have our final topic in Unit 4, which is called L'Hopital's rule. Okay, I know you want to say Le Hospital. It is not Le Hospital. This was a French mathematician, and in French we say L'Hôpital. And how you say L'Hôpital in French, you actually take out the S. So you sometimes see it as that. I don't know what that little caret is called in French. I'm not a French person. Anybody know what it's called? You might take French and know what it's called? I don't know. It's of no importance. Okay, so sometimes you'll see the different spellings. So I typically will simplify it and say hop like that. Okay, so when I apply L'Hopital's rule, I'll just say L-H-O-P for short. So I take the S out. All right, but both spellings are acceptable. L'Hopital's rule, mathematician, French mathematician. He actually gets credit for it, but it actually should go to another mathematician called Bernoulli. It's kind of how life goes, right? Okay, there's lots of fights among mathematicians about who gets credit and who gets published and all that stuff. So L'Hopital actually didn't discover this first, but alas, we call it L'Hopital's rule. All right, there's actually a wonderful song with L'Hopital's rule that I'm not going to share with you, but I'll send it to you. There's a whole musical called Calculus, the Musical. It's wonderful, and this is one of the soundtrack, and it's to the tune of you know, the old '80s song, "Turn Around Every Now and Then." You know that song? Yes. So it's L'Hopital, every now and then I get it, and it goes into the song. So it's great. So every time I see L'Hopital, I'm like, L'Hopital. It's wonderful. So I'll share with you. I'm not going to sing the whole thing, but I'll share with you the soundtrack, and you can enjoy that on your own time. But know that it's a thing and it's wonderful. Okay, here's what L'Hopital's rule is. All right, so very briefly, you could actually even fit it at the top of this page because it's that short. What L'Hopital's rule does is it actually makes limits freaking easy. We're coming back to limits, guys. We haven't done limits in a long time, and a lot of you, when you think limits, like, oh, right? L'Hopital's makes limits super freaking easy, okay? But only in certain cases. Of course, there's always an asterisk. Okay, here we go. Here's L'Hopital's. We're coming back to limits. So remember, this is applications of the derivative. And it's after you understand derivatives, you can go back to limits, and it's an application to make certain limits much easier to evaluate. If you have the limit and you have a quotient, so let's say f of x over g of x. And when you plug in, so remember when you have a limit, a lot of times you're going to first like plug in that value and see what you get. If you get an actual value, that's the limit. But if it yields what's called the indeterminate form, now there's several indeterminate forms. Now remember, indeterminate is not undefined. Indeterminate is a literal math, I don't know. I could figure it out, but right now I don't know. So that first indeterminate form is 0 over 0. It is not 0. It is not undefined. It is indeterminate. That means it could be 0. It could be 1. It could be infinity. It could be -2. It's an I don't know. Okay. So if you get 0 over 0, or there's another indeterminate form, infinity over infinity. Again, not 1, not 0, not infinity, not undefined. It's called indeterminate. Now, there are other indeterminate forms, but these are the only ones that apply with L'Hopital's rule. If at the end we have more time, I'll show you some of the other indeterminates. But if you evaluate a limit and it yields 0 over 0 or infinity over infinity, then L'Hopital's rule applies. And this is what L'Hopital's rule says. Then the limit as x approaches a of f of x over g of x, I know I'm rewriting it again, is equal to the ratio of their derivatives. So if you take the derivative, now this is not quotient rule, I'm not taking the derivative of the whole statement, but if you have two functions divided by each other and you're taking their limit, then, and they get 0 over 0 or infinity over infinity, then you can take the ratio of their derivatives. And what happens a lot of times with derivatives, that might actually make the function simpler. And therefore, you can now hopefully evaluate. Now, what if that doesn't fix it? Guess what? You can still apply L'Hopital's rule, and you can do it over and over again. Let me show you a couple of examples before we get to like the real examples. You can just watch this, or you can write it off to the side. Let's just try a couple examples. What if I did this guy? Let's first of all see if anybody remembers this guy. It's one that I told you to memorize in pre-cal.
1.
Yes, it is 1. Okay, but if you did direct substitution, if you put in 0, you would get 0 over 0, correct? If you directly substitute. Okay, so this is a case where we had 0 over 0 in determinate form, but it ended up being 1. Let's talk notation. Is this ever, oh man, even writing it gives me the heebie-jeebies. Is that ever okay? I can't look at it. It's so bad. No, it's awful. Man, I feel like I committed a mortal sin just writing that down. You can never say equals 0 over 0 or 1 over 0 or infinity. You can never write that. You can only say equals a legitimate number. It is okay to say if you ever have equals infinity, that's okay notation. It doesn't seem like it would be, but it is okay notation. I think I taught you guys, like, you can kind of like a little thought bubble up here. Like I'm putting down my work. I think we did that, right, with limits? It's like, okay, it yielded 0 over 0, and therefore we did something with it. So this had 0, so that's okay. Like that's notation to me. It's not actual like part of my work. But since I yielded 0 over 0, guess what L'Hopital's rule says? That I can take, so I'm doing L'Hopital's rule. So I'm kind of telling my grader that, hey, in this next step, I'm doing L'Hopital. What's the derivative? So L'Hopital's rule says if I get 0 over 0, I can take the derivative of the numerator divided by the derivative of the denominator. Derivative of sine is cosine. Derivative of x is 1. Now see if we yield something that works. Yeah, it's 1. Shocker. Does that make sense? Kind of how that works? That's how L'Hopital's rule works. Let me show you another example that, again, we've done before. Let me do x approaching infinity. I'm bringing back some pre-cal things here. Do you remember this guy from pre-cal? If you're talking about a limit approaching infinity, you're talking about a horizontal tangent line. Sorry, horizontal asymptote, not tangent line. Remember the whole little ditty that I taught you guys? Low over high, high over low, same name. Remember that guy? So if you're approaching infinity, you're looking for a horizontal asymptote. What would this be equal to?
3 over 2.
3 over 2. Did I ever tell you why, or did I just tell you this is a thing? I just said this was a thing, right? Yeah. Why? Why is equal 3 over 2? Because of L'Hopital's rule. Because watch, if you plugged in infinity over infinity right now, what would you get? Never say equals infinity over infinity. We would be getting infinity over infinity. That's a legit indeterminate form for L'Hopital's rule, correct? So I'm just going to kind of show you. Obviously, 3/2, that's a quick route to get there, but I'm showing you why. Why can we do that? So if I take the derivative of that numerator, we'd get 6x plus 4 over 4x minus 3. Okay, we run through again. Plug in infinity. I mean, that's a terrible thing to say. That's why I'm putting in quotations. We get infinity over infinity yet again, correct? Apply L'Hopital's rule again. So sometimes L'Hopital's rule, you're going to have to do it twice. So watch. If I apply L'Hopital's rule again, we get 6 over 4, which, ta-da, is 3/2. Okay, so those rules, the high over low, low over high, same name, they came from L'Hopital's rule. You just didn't know calculus yet to know how to apply. Now, how do we, I just told you L'Hopital's rule, right? But that is a mathematical thing that has been proven. And a lot of times we show you these rules, but the proof involves higher level of mathematics that you haven't learned yet. Okay? All right, any questions on that before we now try these examples here? Okay, so that's L'Hopital's rule. So we're taking a limit, and when you do direct substitution on a limit, you yield 0 over 0 or infinity over infinity. You can take the derivative of the numerator and denominator. Let's talk notation. I already told you, never, ever, ever do I ever want to see on your paper equals 0 over 0 or equals infinity over infinity. The way that I've taught you before is I kind of just did off to the side, like in parentheses. That's great for multiple choice. That will not fly for free response.